Hello to the lecturers and our fellow classmates. Hope you guys doing well in this pandemic moment. I'm Pershian from Group 1. Together with me is my partner Kakit. Today, I'm going to share with you a case study on an explosion happened in an oil refinery plant in Philadelphia. So first, let me introduce to you the plant where the incident happened. Philadelphia Energy Solutions, in short, we call it PES, was located in South Philadelphia, Pennsylvania, in the United States of America. PES owned the largest oil refinery complex on the eastern seaboard, producing gasoline, jet fuel, ultra-low sulfur diesel, kerosene, and many other petrochemical products, with nameplate capacity of 335,000 barrels per day. In general, PES can be divided into two sections, the Point Breeze and the Giraffe Point as shown in the figure on the right. Giraffe Point is a 190,000 barrel per day facilities with operation including crude oil fractionation, catalytic cracking, distillate hydrotreating, reforming, isomerizations and alkylation, as well as aromatic extraction facilities that feed the only cumin unit in the Petroleum Administrations for Defense District 1. The main section that we will be discussing today is the 433 hydrofluoric acid alkylation unit in Giraffe Point. Figure here show the process flow diagram of PES hydrofluoric acid alkylation unit. This hydrofluoric acid alkylation unit is used in the petroleum refinery to convert isobutane and alkenes into alkylates, which is used to make gasoline. In brief, propane, butane, butylene, and isobutane from the upstream processes will be sent to the treater feed search drum B1. Before being transferred to the alkylation unit, the feed will pass through caustic scrubber and deethanizer to remove hydrogen sulfide and ethane. Once in the alkylation unit, the alkenes react with isobutanes with the presence of hydrofluoric acid catalyst, creating alkylates. Alkylates and remaining hydrocarbons that separated from the hydrofluoric acid catalyst in the hydrofluoric acid settler will then undergo downstream refineries. Overhead of depropanizer containing propane product and hydrofluoric acids are condensed and separated in overhead depropanizer accumulator. Section of hydrofluoric acid containing propane are returned to the column while remaining is stripped free of acid in propane stripper. Bottom of propane stripper is acid-free propane product which is treated with hot alumina to remove organic fluorides. Cold and treated with potassium hydroxide pellets to remove traces of hydrofluoric acid and water. Distillate and section of alkylates and hydrocarbons from the hydrofluoric acid settler will then enter into isostripper. Overhead isobutane and propane will be recycled for alkylations, while bottom will be entered into the debutanizer to separate alkylates and butane product. The rapid acid de-inventory RAD system will serve to de-inventory the bulk hydrofluoric acids from hydrofluoric acid settler to RAD drum. On June 21, 2019, 4:02 a.m., during the plant normal operation, a major process loss of containment causes a fire and explosion at the 433 hydrofluoric acid alkylation unit in Giraffe Point. Post-investigations shows that the rupture of elbow between the depropanizer accumulator and the depropanizer distillation column appeared to be the initiating event causing the process fluid release. This fire raged for more than 24 hours, releasing 5,239 pounds of deadly hydrofluoric acid into the air. Next, I will explain in detail on the incident timeline. This three explosion incident timeline was summarized in the table here. During the early hour of Friday, June 21st, the hydrofluoric acid alkylation unit was reported to be operating normally. Right after 16 seconds past 4, there was a sudden loss of containment causing flammable process fluid containing hydrofluoric acid to release from the PES alkylation unit, forming a ground-hugging vapor cloud. At 4:02:06 a.m., the flammable vapor cloud ignited, causing a large fire in the alkylation unit. After 30 seconds, the control room operator activated the RAD system, which de-inventoried the bulk hydrofluoric acid from the hydrofluoric acid settler to the RAD drum. At 4:15 a.m., during the ongoing fire, an explosion occurred in the alkylation unit. A second explosion in the unit then occurred after 4 minutes. At 4:22 a.m., a third and the largest explosion occurred when the V1 treater feed search drum containing primarily butylene, isobutane, and butane violently ruptured. A fragment of the vessel weighing approximately 38,000 pounds flew across the Schuylkill River, and the other two fragments, one weighing about 23,000 pounds and the other about 15,000 pounds, landed in the PES refinery. This appeared to be the secondary event caused by the fire. The fire was extinguished on the following day at about 8:30 a.m. Photo here illustrated the actual scenario during the incident. The incident scene of pre and post incident was compared as shown in the slide here. As noticed in the figure on the right bottom, V1 was gone due to explosion and V6 has been pushed to the right. Following that, I will share with you on our findings in the technical details of the unit operations in the incident. The table here shows the chemicals involved in the unit sections, which indicates that flammable chemicals are present in the unit. Prior to the incidents, a latest hazard was conducted on June 28, 2017, and the hazards identified and installed safety features on the unit sections was shown here. Investigations by the United States Chemical Safety Board says that Philadelphia explosion was occurred due to a corroded pipe elbow in the refinery explosion unit. The elbow was part of the piping between the depropanizer accumulator and the depropanizer distillation column in the refinery. During incident, the piping was operated at a pressure of about 26.2 bar and a temperature of about 37.8 degrees Celsius. Approximate design compositions of process fluid in the piping contain 94.7% of propane, 2.5% of hydrofluoric acids, and 2.8% of additional hydrocarbon. Next, regarding the safety measures for pipe thickness in the site, the piping circuit with the ruptured elbow was subjected to regular ultrasonic thickness measurements at designated condition monitoring locations (CML) as part of the site inspection program to monitor the rate of piping metal loss due to corrosion. Most pipe thickness in that section of the unit was periodically measured to monitor corrosion rates, but the thickness of elbow that failed has not been monitored for corrosion. Figure here shows the model of the piping circuit containing the ruptured elbow. The most recent thickness measurements at designated CML are shown, along with the year of each measurement. At the time of incident, elbow was on the discharge outlet piping from a pump that was not operating. This figure also illustrates that Triton fish search drum was directly above the ruptured elbow. The ruptured pipe elbow was found after incident. The thinness measurement taken of the ruptured elbow after the incident was only 0.012 inch, approximately 0.3 mm, which is less than 7% of the PES default retirement thickness. Detailed investigation on ruptured elbow by CSB shows that the piping circuit containing ruptured elbow was installed in 1973. The piping circuit was constructed to meet 1965 version of ASTM A234 of grade WPB material specification. ASTM stands for the standard specifications for factory-made wrought carbon steel and ferritic alloy steel welding fittings, while WPB is a steel grade in which W is weldable, B is grading B, and P is pressure, thus referring to the minimum yield strength of the material. The 1965 version of ASTM A234 at the time of pipe installations required that grade WPB pipe permissible raw materials compositions to meet the A106 grade B chemical composition specifications. However, the 1972 ASTM A106 standard did not specify the nickel and copper compositions requirement. In 1995, ASTM A234 began to specify the nickel and copper compositions as well as compositions of other elements. The WPB compositions requirements in 1972 and 1995 and the chemical compositions of the ruptured elbow and the adjacent elbow are shown in the table. Unfortunately, the nickel and copper content of ruptured elbow exceeded the updated A234 WPB requirements that specified in 1995 as highlighted in pink. American Petroleum Institution recommended practice 751 safe operations of hydrofluoric acid alkylation units states that the hydrofluoric acid corrosion has been found to be strongly affected by stale compositions and localized corrosion rate can be subtly affected by local chemistry difference. They also states that the combinations of carbon content and residual elements content could increase non-uniform corrosions by up to 5-fold compared to baseline measured corrosion rates. In layman terms, this means that high nickel and copper compositions in the carbon steel causes the pipe to corrode at a faster rate than those of lower percentage in the process with hydrofluoric acid. That's all from me. Next, I will pass to Kaki to continue on part 3.
Good day everyone, my name is Lee Kaki and thank you for giving me the time to explain my part to you, and thanks Rachel for introducing me also. So now I'll continue the presentation by going through the local laws, regulations and compliance regarding to these incidents and this refinery plant. So from what you can see here, this National Emphasis Program, which is given by OSHA Directive. So from what you can see from this table, this is the table of what you are required to submit to the OSHA Directive when you are trying to get your plant going. And so from an internet source, which I acquired online, which shows all the submission of this Philadelphia refinery. It's shown that some of the criteria, such as management of change, contractor safety, incident investigation reports submitted by them are very vague, means that it's not clear, it's not as detailed as it's supposed to be. So, for example, for the management of change, you're supposed to submit every time there's a change in your plant or anything's happened to them. So this is actually not the first time that Philadelphia Refinery actually have an accident. So a few months before this current June accident, they actually have another accident, which the internet sources believe that actually they didn't imply these changes to the employees and the workers. So this is not safe, and it's actually advised for the OSHA for them to keep up the changes and practice this habit and share all this information with their workers. So moving on, we look at some of the basic standards and enforcement laws regarding to labor. So regarding to labor, this would mean that it's about the labor forces, the employers, and the employee themselves are related. So first up would be the OSHA standards. OSHA standards is actually not a very strange term, and I think we are very familiar with this as we've learned this before. So what OSHA standards is actually the general duty clause of the OSHA Act, which is the law that created by OSHA. So this requires the employers to provide workers with a safe workplace. Basically, we are guided by this OSH Act to create a workplace that is safe for all the employees. So next would be the general industry. So this general industry 29 CFR 19 and 10 is actually also a guideline given by OSHA. But instead of OSH Act, this is called general industry guidelines. So these are some of the guidelines which contain a lot of subparts. So some of the subparts that I've highlighted here are those regarding the toxic hazardous materials, some of those that related to the fire protection, hazard communication, which is very important in the case of incident or anything dangerous happening inside the refinery plant. So moving on will be the letters of interpretation. So what letters of interpretation means is actually also a site guideline provided by OSHA. In this case, it's provided by OSHA to further guide the refinery plant employers when they're trying to design or they're trying to get their plant working in what they need to keep in mind or what they need to keep track as the time goes. So in the letters of interpretation, there are also a lot of subparts. Some of the subparts that I highlighted regarding to this incident is the fire explosion. So in the case of fire explosion, there are a few guidelines or policy that you have to follow using these letters of interpretation. Some of it being the clothing of the workers, or what you're going to do with the liquids and which are flammable and combustible, and some of the PSM elements that you're supposed to have in the case of any combustible or flammable liquids existing in your refinery plant. Although not that common, but you still need to keep in check are the Bureau of Alcohol, Tobacco, Firearms and Explosive, which is 27 CFR 555 Commerce and Explosive. So I've listed the scope in below, but let's move on to the next one. So some of the other more important will be the national consensus standards. These are standards not set by the OSHA themselves, but actually standards that are set by the national regarding to the conduct of a refinery plant. So we can look at this one, the National Fire Protection Association that give up NFPA 1, 10, 30, which is most of them, this is all related to the fire protection and some of the hazardous materials that will cause fire. So moving on will be the API, which is the American Petroleum Institute. Like what I said just now, API is actually a voluntary guidelines that is existing to provide a guides for the refineries, but they does not necessarily have to follow it. They are just advised to do it, but most of the refineries are actually following the guidelines because it's a safe practice of the engineering ethics and stuff. So first up will be the API refining program. So this refining program is actually developed by the committee that they give the practice in the design, fabrication, installation, inspection, and all the other equipment. This includes the inspection of the equipment, some of the pipings, the corrosion, which are all crucial in the running of a refinery. Next up will be some of the example of API standard that I've listed up here. Another refining program that I would like to highlight would be the RP751. So RP751 was also mentioned by Hui Shen just now. So this area specifically cover the materials, the construction inspection of any HF units, as well as those inventory controls, relief, and utility system. By following this RP751, we can see that the corrosion materials considerations specific to the HF calculation unit. Next would be EPA, Environmental Protection Agency. So two of the standards that we'll be looking at now. First one being the EPA Renewable Fuel Standard, which is a quite recent standard actually from 2005 as compared to all the others in the previous. So what happened is that this policy requires a certain volume of renewable fuel to replace or reduce the quantity of petroleum-based transportation fuel. Now, at first glance, this is actually a standard where it makes to look the world greener or makes to look the production cleaner in a sense. But at the same time, this also skyrocket the cost when you're producing a fuel. So moving on, we'll come to this hydrogen fluoride study on 1993 conducted by the EPA. Philadelphia was trying to blame EPA for making the fuel cost production increasing in these past years, which caused them to have to stay in the reliance of using HF calculations during the production of their products. There's actually a few incidents in the previous years that was actually caused by this same HF calculation. So the CSB, or the US Chemical Safety Board, actually called for a restudy on this HF conducted by EPA to see that if the existing regulation, is it still effective or should they be updated to prevent any more major incidents like this to happen again. So during the 1993, it was stated that HF is toxic by contact annihilation. They are very toxic, but although being very toxic, these properties does not call for any unique precautions stated by EPA. Now the reason because of this was during 1993, most of the refineries or most of the fuel production units are relying on HF. So let's move on to this HF alkylation. So alkylation is actually a very hazardous chemical process. When you're using HF, this process gets even more dangerous because HF can radiate from dense, highly toxic vapor, which is what happened in this incident. Next would be the safer alternative to this HF alkylation. Now in the past few years, a lot of plant and oil refineries are actually trying to not rely on HF. So some of it being the ionic liquid alkylation process, SAC, solid acid catalyst alkylation system, or sulfuric acid alkylation. So all of these are actually IST, which are inherently safer technologies, meaning that you actually substitute the HF with another less dangerous chemical. Now sulfuric acid alkylation was one of the other major refinery option in US, but it's actually still not recommended as well because sulfuric acid is also very toxic and hazardous. Now, although there are much safer technologies being introduced throughout the years, but then there's still many small refineries or many major refineries still relying on the HF alkylation. So the reason why when there are actually safer technologies but people still rely on HF alkylation is because of they got away with the OSHA violations during the PSM inspection. Now this is very common not only in refinery but in many other industries also. The second reason being the profits that you're able to gain by using the HF alkylation. As I've mentioned above, HF alkylation has been the more traditional way or has been the cheaper approach in their fuel production or refinery production. So by maintaining as the HF alkylation, you do not need to invest on this new safer technology. So next up will be a table of recommendations, including all the safety elements that from our group we recommend to this Philadelphia incident. The Philadelphia or other in the future refineries should closely monitor their corrosion monitoring, not only just on the main pipes, but also on the elbows or any pipelines that will relate to the transportation of the HF itself, and also effectiveness of the safety system for HF related process. There's also need to be a leak detection and repair in a very close schedule. Also the emergency mitigation and response system in this case, they need to provide safe havens or to provide a site where the employees can take their cover, because from this incident, there's actually 5 workers that suffered injuries, but then the injuries of the employees or any worker should be avoided at any cost. Next, the fire suppression system should also be improved. Next, remotely operated block valve should also be included in the isolating HF unit so that the HF units and the pipelines can be isolated immediately in the case of any leak detection or any vapor cloud forming. From this incident, the surrounding neighbors of the Philadelphia actually suffered from some of the health impacts. Example of them are the birth outcomes or the increased rate of the cancer. Some of them also suffer from anxiety. And actually from the news, there's actually 2 individuals from the neighborhood that was killed during this incident. So it's important to remind all the refineries and industrials designers that PSM is very important because you're not only governing the safety of the industry, but you're also controlling the safety of those surrounding you. So in this last slide, I would like to showcase one of the safety case regulatory regime that people can follow in designing their PSM. Thank you so much, and please leave us some questions if you have any. Thank you.